And here we are again for part 2. So let's talk about frames versus trusses. Frames versus trusses. We saw previously that we learned the definition of a truss. What is a truss? What is a truss? Straight members joined by yes, exactly. A truss is composed entirely of straight members, pin joints with loads only at joints. I could probably add one other thing too that I didn't cover last time. Straight members, pin joints, loads at joints, and I would probably say that members terminate at joints. Members terminate at joints, so we're only applying loads at the member ends. So basically, therefore, loads only applied at member ends. Loads are only applied at member ends. Frames, some of these assumptions break down. Some or all of these assumptions break down. Break down, or are no longer applicable. So largely we're still going to be concerned with pin joints in this class. When you start dealing with fixed joints, then that's more of a topic for structural analysis or mechanics of materials. But you might see a rare fixed joint in this class, but rarely. Anyway, so you can have loads can be applied to the middle of members at the middle of members. And members can be continuous through joints. Through joints. So I want to show what this means. So loads can be applied to the middle of members or anywhere along them, not just at the middle, obviously, or anywhere along their lengths. So in trusses, we're only applying forces at the ends of members, at the joints, essentially. So, all right. You got that? Okay. Oh, okay. So for example, actually, well, I'll wait then. Got it? Okay. So for example, what could we have? These are all examples of frames. Some of these are things that we will not analyze in this class because they're maybe too complicated, but that's okay. So look what we have here. Oh. Or maybe I'll draw it more like, sorry about that. Didn't want to erase quite that much. This would be an example of frame with fixed joints. But with pin supports. So this would be an example of a fixed joint frame with pin supports. Fixed joints are those that can transmit both shear and moment. and axial force. But we're mainly going to be concerned with pin joints. So what can we mean by that? Let's see. Let me show you something with pin joints that would still be a frame as compared to a truss. I need to make sure I draw this top one right. It's the key one. So say I had something like this. You'll definitely want to read your book about this. This goes into the theory deeply. Like this, and like this. Say I had something like this. This is a frame. Why is this a frame as compared to a truss? Why is this a frame instead of a truss? Yes, exactly. The member, one of the members is continuous to the joint, through the joints. See here, this member here, the top vertical member, continues all the way through the through each of these joints. So what you would need to do then is, it actually, I meant to actually show this extending a bit beyond there, so that's okay. So the way you handle this is in frames. Anytime a pin joint is applied, or is connected, I should say, is connected in the middle of the member, the interior, remember, of a member, an X and Y internal force will be applied. Okay. So for example, on this one here, what would we have? So this is A, B, actually, you know what? B, let me call the end of this C, D, E, and F. Okay? So let's look at this. I would have member AC. So I would have A, C. Really, this is, do you remember that one problem a few days ago where we had the, I believe on Monday, where we had the things that were like that on the slope? Remember that one? That was sort of an introduction to frames, you might call it. This one, actually, this should actually be B. If this part here is B and this one over here is C. So this would be member AB. Then we would have member CBDE. So I'm going to draw it, and then I'm going to draw this, then I'm going to show the forces on it. C, B, D, E, and then I will have member DF, D, and F. So we need to draw this with internal forces, and we need to show compatible forces. So the first thing I'm going to have is my reactions, AX and BX, or sorry, AY, sorry, and AY, my FY and FX. Then I will have bx like here, by here. But again, when I draw this, I need to draw these with compatible forces. So I drew this bx going to the right, the corresponding bx on this portion needs to go to the left. Bx and a downward by. They must occur in equal and opposite pairs. So dx, dy, and then this one will go to the left, dx and dy, like shown. And from these, we can then solve for all of our internal forces. So the method of analyzing frames is to break it into pieces. You need to break the frame into pieces and apply internal forces. Every time there is a joint, there will be internal forces. So there's a certain amount of practice that you'll need to gain with this, but this is the basic idea for analyzing frames. We break a frame into its constituent pieces and apply internal forces as necessary to keep it in balance. So that is the basic idea, and the rest is just math. All right, questions on that? Okay.
What were you saying occurs in pairs?
What occurs at pin connections, you'll have these two forces in pairs. Okay. Yeah. So actually, let me show you the types of internal connections you can have. Types of internal connections. Types of internal connections. I'll just go ahead and show them to you. But you probably won't see the fixed that often in this class, but just so you're aware of it. One, you're mainly going to see you're mainly going to see pins, but occasionally you might see a roller. Roller connections. Roller connections. Okay. A roller connection, if we're talking about simple machines, is going to look a little bit different than a roller connection you might see otherwise. Here. So say you had two members like this, and there's a member here with a slot in it. Then there's a pin in here. And the other member is joined to this like here. Like this. What this means is that this can transmit an internal force only in one direction, the direction perpendicular to the slot. See, if it tries to transmit a force in this direction, the pin is just going to roll. So I would call this an internal roller connection. So something like, so if I look at it just in terms of lines like this, if I just draw my members as lines, I will have say this is point A, for instance. The only forces here would be AY and AY, like shown. They would only transmit one direction of force, but still they need to occur in matching pairs. 2, we can have an internal pin connection. This will be the most common that you'll see in this level of class. In the real world, we design structures usually with a mix of pin and fixed connections, but this will be the one that's most common in this class. So it's what we saw previously. A pin can, so maybe I can actually say, transmits force, internal force one direction, perpendicular to slot direction. Now this one can actually be kind of tricky because especially if, imagine the slot is at an angle, then you'll have a reaction force that's at an angle, or internal reaction force that's at an angle, and it can get a little fun to calculate that. A pin connection transmits X and Y internal force. So if you have a member that is joined up with another one with a pin, it can transmit force. So this is point B. This can transmit force. Let me just draw these again as line members. Like you can either draw, sometimes we draw members in structural engineering as, or in civil engineering, we sometimes draw them as drawn out. Sometimes you just draw them as lines. But anyway, depending on what you're doing. So point B here. So let's say we have point B here. And then we have this member here. This is an exploded diagram, basically. We would have Bx and By, and then on the corresponding piece, we would have opposite forces, Bx and By, like shown. Okay, simple enough. Again, the pin can transmit force in two directions. And finally, what do you think the last one is? Fixed connection. So these are basically these are sort of correspond to the supports. This is a roller connection, a pin connection, and a fixed connection. Will you see these at all? Uh, you'll definitely see the pin and the roller. You may not see the fixed. There may be a few in the book. Let me see. There may be some. There's probably actually there may be some. Yeah, depending. Sometimes you see them, but they're not very. At least at this level, in a statics class, it's difficult to design a problem that's solvable by statics non-trivially that can have fixed supports in it, fixed connections in it. So it's going to look something like this. Transmits fixed connection, pin connection, roller connection. Transmits X and Y force, internal force, and moment. So you have something like this. Say you have two members coming together at joint C. They're literally just continuing one right into the other. So the way we draw this is, say we have member this one here and this one here. I would have Cx, Cy, and My, Cx, Cy. Oh, thank you, MC. Thank you. That should be MC. That would make a little more sense. MC, Cx, Cy, and I want to make sure the moment's going in the opposite direction here. MC. And there you have it. So I would set up my equations of equilibrium using moments in that direction, using end forces in those directions. And those are the three types of internal connections that you are likely to encounter. All right. And also sometimes you see things like pulleys and stuff like that, but those aren't really connections, more just components and things like that. Yes? You could also apply it if they weren't at a perfectly right angle. Huh? Yes, the same thing would apply whether this was at a right angle or not. In fact, let me just illustrate that really quickly once you've finished copying down. I mean, I could just as easily have this at a non-right angle and the same thing would apply. Okay. The only thing that the big thing that would be different is when you go to do like a balance of moments, then the on that piece, then things would turn out a little different. Okay. Good. Okay. Okay. So methods for solving frames. Let me just give you a general method for solving frames. One, if less than 3 external reactions are present, solve for reactions treating frame as a rigid body. Okay. Then 2, draw exploded view. Showing external and internal forces and reactions. And reactions. And 3, use sum of forces x, sum of forces y, and sum of moments on individual pieces to solve for unknown forces. Solve for desired unknown forces. Unknown internal or external forces. Or external forces. And you can read much more about this in the book. It does go into the theory a lot deeper than we'll quickly cover here, but that's just the general method. That's the basic method we are going to use to solve simple frames. Yes.
Do all frames have just straight members?
Mm. Question, do all frames have straight members? And sometimes no. Absolutely not. You don't need to have that. You can find some examples in the book. For example, on page 324, number 6.81, I can see a member that's curved, or at least bent. So yeah, you can have some classic examples of things that get an example of something I see a lot in books like this. Sometimes you see example. Oh, there you go. I was looking for this. On 3.31, there's a pair of pliers, and you can analyze that as a simple frame, and or a simple machine in this case. But that's the idea. So,
And also, what differentiates a frame from a machine?
what differentiates a frame from a machine? I would say usually a machine is some compact object used to get mechanical advantage of some sort, generally. But in terms of simple machines. But the book may have a slightly different definition. Let's see. Let's see what they say the difference between a frame and a machine is. Yeah, they're talking about in terms of input and output forces. So yes, it's something to get mechanical advantage. Okay, questions on this theory? Okay. What do we have here? What do we have here? For the frame and loading shown, determine the components of all forces acting on member ABC. All right. How might we do this? So first, let us solve for the reactions. There's definitely many different ways we could solve for this, but I'm just sort of going to take a wandering, meandering approach and sort of hope to come to the solution. So let us say we have EX here, AX, and AY, and AY, AX and AY here. The reason I did not put an EY is because if you look closely, this is a roller support, and this is a pin support. Here. So now I'm going to do, say, well, first of all, let's see, I could just do a summation of forces in the vertical direction. This is on the global free body diagram, treating the entire object as a single rigid body. So it'll just be AY minus 20 kips equals 0, which of course leads us to that AY is equal to 20 kips. Then I will do the summation of moments about points A, and that gives us EY, positive moment, counterclockwise, times 4 feet, minus 20 kips, times 5 feet, equals 0, and EY, actually let me put it over here. I want to try to save space, conserve space. This leads to EY is equal to, this is going to be 100 over 4, so 25 kips, correct? 25 kips.
EX.
Oh, yeah, EX, EY. Hey, I was within 90 degrees, right? Oh boy. I was within 9 degrees, close enough. Close enough for government work. Um, huh? Oh, okay. Summation of forces in the x direction then is AX plus EX equals 0. And then from this, I can get that AX equals negative EX or negative 25 kips. So there we have it. Now, let's see. I'm trying to think of a useful approach for this now. Now, let's see here. Now, these members here and here are still going to have the same behavior of one thing we can harness is that this member here, EB, is still going to demonstrate only one force because the conditions of trusses, the conditions on trusses on pin member supports still apply, right? The conditions there still apply. In that if you have a generic member, any member with pins on both ends, this member must carry either a tension load or a compression load, and that's it. So we can actually use that to our advantage. So I then am going to I want to get the force in member EB. So let's consider joint D. Or sorry, joint E, sorry. I'm just sort of looking ahead at where this is going to go. All right. So say we have, let's see. Well, we have EX, right? EX. And then we're going to have, actually, let me write this as, let's see here, FBE. Trying to think if this will help us or not. Let's see. Maybe. Let's see. See, this is what this is going to look like. And then, because the issue we're having is, if I try to draw it like this, with a simple connection like this, that's true, but unfortunately we also have this EX here, so we do have to consider the individual joint. So, but this thing here is capable of transmitting both a horizontal and a vertical. So there's got to be a better way to do this. Let me think about this for a second. Huh? Forced triangle. We could do a forced triangle, but again, the problem is this. The problem is this member here. So let me. Actually, no. Wait. Never mind. We're good. Let me. Sorry about this. This is obvious. Let me back up. I need to consider member ABC. Member ABC is actually very clear now. It may not seem that way, but it is. So sometimes you do have to play with these a bit until you kind of get it. A, B, C. Now, let me show the forces on here. And the forces on here are going to be, let's see, they're going to be the AX here, which is actually a negative 25 kips. So to the left, 25 kips. An upward force of 20 kips, AY. AY. And then down here, I'll have CX and CY. And then here, I'm going to have a BX and a BY, right? We have this internal pin here, so we have the BX and the BY. However,
How are you choosing your directions?
just a completely, the question was, how am I choosing the directions? Completely arbitrary. I'm just initially assuming everything's to the right and upward, and if I were to draw member EDC, the corresponding one would be down and to the left for this C force here. Now, I do need, see, just looking at this, I have a problem. What is that problem as drawn? I have 4 unknowns. I need one other known. I need one other equation of equilibrium. And the way I'm going to get that is that I have a hidden relationship here. I know a relationship between Bx and By. I know that these must distill down to a single force that acts along this member because it is a pin-pin member. Huh?
I guess we just call FB.
Yeah, FB. So, in other words, there's this FB that, let's see. And you know what? How do I want to draw this? I probably want to draw this. Let me draw this here. We're going to have to play with the directions a bit. No, it doesn't really matter. I'll just say that there's a total FB here. That is a, well, let's see. This is a 5, 4, and then square root of that. Square root of 5 squared plus 4 squared is 6.402 or 3. 6.403. Oh, sorry. Yeah, you're right. You're derp. I gotta do a little trigonometry, don't I? Oh, that's 2, don't I? That's just 2. Let's get your trig right. 2 So let me show this. And then,
It's 2 because you kind of just looked at it and cuts halfway.
yeah, it's 2 because it's clearly half. And 5 point, let's see, 5 point, let me think about that. Just want to make sure that's, yeah, 5.385. 5.385, right triangle. And this is going to be proportional to, here, this is going to basically be proportional to a FB. I'm not terribly concerned with I'm not wasting a lot of time thinking about the directions. I'm just going to say this is proportional to this triangle here, like this. Like so. Yes?
Would that only work on joint B?
Yes, this only works on joint B. And there, again, the reason we're able to do this is because it's a pin-pin member. And both of these forces must distill down to a single force that acts along there, that acts along member EB. Here on this member, it's a lot more complicated because we're going to have we have this force applied at the middle of the member, which means that if I were to draw that this member is going to carry shear, moment, and axial force. It's going to carry shear, moment, and axial force. Okay, I probably should mention that here. Let me go back and give a quick demonstration. If you don't know what those are, let me give you a quick demonstration. Shear, moment, axial force. Oh, moment and axial force. And this connects with what we'll see tomorrow on member internal forces. If you have a generic member, the types of forces you can have on it, or in it actually. You have your shear V, which is a force, an internal force that is transverse to the member. You have moment, M. And you have axial force, A. A or F. So I could say, just F for now. In truss members, there's only this F, this compression or tension. In frames, you can have shear, moment, and axial force. So shear is a force that wants to cause a member to shear apart. Like imagine this thing breaking here into two pieces and this piece going this way and this piece going this way. It wants to shear apart. Axial force wants to pull a member apart along its length or compress it or cause it to collapse. Moment wants to cause a member to bend like a smiley face kind of thing or a frown shape, something like that. So these are the internal forces in a member. Now, if you apply pins on either end of a member, as in trusses, we have seen that this simplifies the problem greatly. By putting pins on either end of a member, you completely eliminate the shear and moment in a member. And so we never needed to consider shear and bending moment in trusses. But anyway, in simple machines and frames, we do. So in this case, again, if we were to draw draw member EDC, we would have to draw the end forces. We could not simply say they're going to reduce down to a single axial force because this member may carry shear and moment. Okay, but anyway, essentially what this member gives us is a new equation of equilibrium. What we now know is that Bx over By, or not an equation of equilibrium, just another equation, equals 2 over 5. Or I could say, if I wanted to, Bx equals 2/5 By. And that will be an equation that we can use. So now let me do the sum of, okay, so I know I have this one and this one. So we've already solved for the two. Actually, that's this right here is two of the things the problem is asking for. So let me do a sum of moments about, say, point C. I'm trying, basically I have 4 more unknowns, and that is why I am solving for, actually, let's think about this. Okay, now we're good, we're good. Sum of moments about point C. That will eliminate these two as unknowns, and I will then have 20 kips, negative moment, negative 20 kips times 10 feet. Speaking of 20 kips, plus 25 kips, 25 kips times 4 feet. So let me kind of cordon this off here. 25 kips times 4 feet, positive moment, plus bx, or actually, let me do a no, minus bx, minus that, sorry. Minus bx times a distance of 2 feet, minus by times a distance of 5 feet. And all of this equals 0. Okay? And then I can go and say, all right, I want to perhaps replace, yeah, something like that. Or I could also say, you know what, just for fun, I'm going to say by equals 5 halves bx. So negative 2bx minus 25 over 2 bx over 2 bx equals 0. So then I bring this over. Actually, no, wait, something's not right. Oh, wait, I have a big problem, don't I? Oh, no, I don't. Wait, let me think about that. Never mind, I'm good, sorry. I'm forgetting my forces here. Derp, it helps if you do the right force. Huh? I'm still need those. Wait, what are you talking about? Or just these right here I need, right?
It's about C. Make a
Oh, yes, 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 yes. I need my, thank you, thank you, thank you. I do need my 20 kip force. Sorry about that. Forgot that. Plus 20 kips times 5 feet equals 0. Okay, so first let me get rid of all the constants. Negative 20, or let me combine them. Plus 25 times 4 plus 20 times 5. Oh, wow, that's not good. Well, that's not any good. 5 over 2? This, are you having a problem with this right here? Or over here? What are you having contention with?
size of the triangle in there. For bx over by.
Bx over by.
Should be 5 over 2. That's what's from this.
2 over 5 equals, oh, by over bx, yeah, yeah. Derp. Sorry about that. Just having all sorts of math errors today. By over bx. Which, I'm having a bigger problem with the other expression over there. Just a second. Let's see, over bx, and from this I can get by equals 2/5 bx. Okay. Now here, do you see the problem here? See, all this, the real problem is that this stuff comes to 0. See, wait, no. Yeah. See, negative 200, negative 200, let me just double check this. Negative, negative 20 So that's definitely a negative moment. Negative 20 times 10 plus 25 times 4 plus 20 times 5. And you see all of these come to 0, which is not going to help me. See, these forces come to 0. This plus this plus this is 0. So I just end up getting bx, the moment generated by bx and by comes to 0. That's not going to help me. I can't solve. That doesn't give me any useful information. So I'm actually going to have to first solve for moments about b first, I believe. Unfortunately. Okay, so let me do the sum of moments about b instead. Sum of moments about b. I'm going to have first ey. Oh no, not ey. We don't have to worry about that. Oh, derp, I'm an idiot. Sorry. There's a reason I left out the 20 kip force. We do not need it. No wonder why we're having problems. Sorry, I have to rewrite that. We don't need that 20 kip force. There's a reason I left it out to begin with. Never mind. I thought we were in deep trouble. We're not. Moments about C. 25 kips times 4 feet minus AY times 10 feet. Oh, let me call that. AY is the 20 kips minus 20 kips times 10 feet. Here, AY times 10 feet. Minus BX times 2 feet plus BY, or minus AY, sorry. Let's see. Yeah, 25 kips times 4 feet. Wait a minute, something's still not right. No, we're good, we're good, we're good. BX times 2 feet. Yep, negative moment. And BY also negative moment. Minus BY times 5 feet. And all this comes to 0. Okay, the reason we don't need this 20 kip force is this force is not applied to this member. This force here is not applied to member ABC. It does experience a force from it, but that force is carried through the reaction CY and CX, and through a bit here as well. So we don't need to worry about that. On our balance of moments, we are only including the forces shown on the free body diagram of that member. So I'm then going to say this is positive 100, negative 200, negative 100, and then minus 2bx, and then by is 2 over 5bx, so this just becomes minus another 2bx equals 0. So this reduces to, let's see, negative 4bx equals 100, bx equals negative 25 kips. And in turn, by equals negative 20 kips. Sorry, negative 10, yes, negative 10. Derp. One of those things, 10, 20, same order of magnitude. Negative 10 kips. So we have that one and that one. And then finally, I can simply do a sum of forces in the x direction equals bx minus 25 plus cx equals 0. And from this, I will get that cx equals 25 negative minus negative plus 25, right? So I think 50 kips for cx, if I math correctly there. So again, minus 25, but this becomes a negative. Minus negative is a positive. So 50 kips. double check that. Let me think. Wait a minute. BX, you know what? I'm just,
50 kips.
positive 50?
Yep.
Okay, we're good. So yeah, CX is positive 50 kips, or 50 kips to the right. And then finally, summation of forces in the vertical direction is 20 kips. BY will be a minus 10 plus CY equals 0. And from this, we can get that CY equals negative 10 kips. Like so. And that's our final answer. All right, questions on that?
Can you state that again? Like, so we make the free body diagram, and you said no forces that are not acting on the free body diagram will be included in our moment.
Yes, again, the only forces that will show up in your sum of forces calculations or your balance of moment calculations will be those that are present on the free body diagram of that member. Okay? We are not balancing forces on the entire structure. We're only balancing forces on that member in this point of analysis.
And it will always ask for a specific AGD, or AG.
Sometimes not. Okay. All right, other questions? Yes.
So on this member ABC, could you, the BY and the BX had the components of each individual force for a point. Isn't that like the same for like FBE, the force along the member?
Yes, it is but it's still sort of two unknowns in the fact that it's you could the question was, isn't this sort of like a single force? In the same way, this is sort of like a single force, yes, but it's just two different ways of expressing the same thing. We could say this is a CX and a CY, or we could say it's a force and an angle. In both cases, it's still two unknowns. Other questions?
So, could we have also drawn like FBE coming out and then a force triangle?
FBE
Free
coming
body.
out, perhaps.
The reason we're
Perhaps.
not,
Yes,
the reason we're separating them into components like this is to make the moment calculations easier, right?
precisely, yes. Yes, the reason we're separating them out is to make the moment calculation easier.
Okay.
All right, other questions? Okay, if that'll do it, I think I have another example I'd like to work through at some point, but I think I'm kind of running short on time. So I think I'll let us out a little early today. Take a look at the homework. I imagine we'll be working through a lot of this stuff tomorrow and also moving on to shear and bending moment diagrams. So that'll do it to take a look at those problems tonight. Remember, the test is on Tuesday. I'll see you all tomorrow, and as always, thank you.